some idea of when an airplane's going to fly and when the airplane's going to stall. It's what makes it fly and what makes it stall. Well, if you study this beautiful example of aerodynamics for a while, pretty soon you gather some insight to it, and you are going to know exactly what makes an airplane fly after studying this for a while, and I'm sure you figured it out by now. What makes an airplane fly is money. And with enough money, you can even do something like this. Isn't that incredible? Well, obviously, that's done with thrusters that point down, not at all like most little airplanes fly. So let's you and I take a look at a little airplane and see how it flies. First of all, there are 4 forces acting on an aircraft. The FAA calls these 4 aerodynamic forces, and those 4 forces are thrust, which makes the airplane go forward, and drag, which tends to slow it down, and weight, which wants to make it go down, and lift, which wants to make it go up. So the 4 forces acting on an aircraft are thrust, drag, lift, and weight. Now, let's assume that you and I have this airplane flying along in straight and level flight. It's not changing speed, and it's not changing direction. Well, the FAA has a term for that, and that term is that the airplane is in unaccelerated flight. That means it's not changing speed or not changing direction. Now, the FAA says, all right, let's assume that this airplane is in unaccelerated flight. What is the relationship of these 4 aerodynamic forces? And the answer is they are in equilibrium in unaccelerated flight. Now, equilibrium means thrust is equal to drag, and they are not changing. Lift is equal to weight, and they are not changing. So in straight and level, unaccelerated flight, these 4 forces are in equilibrium. They are equal to each other and not changing. So the relationship in straight and level flight is lift is equal to weight, and thrust is equal to drag. Now you've got some idea of the 4 forces on the aircraft. Let's you and I talk about what actually creates the lift that makes an airplane fly. We can refer back to a guy named Bernoulli, I guess I should say, who I am told was Swiss, who did some experiments. And what he did is he forced moving air through a narrow point in a tube. Now, a narrow point in a tube is called a venturi. And he put some gauges in here, and he measured the air pressure as it went through this narrow point in the tube. Now, he found what I think is really fascinating things when he did this. What Bernoulli found is that when the air got to a narrow point in a tube, it has to speed up. And the interesting thing he found is with the gauge, he measures the air pressure where the air is going the fastest. And what Bernoulli found is at points where the air is going the fastest, the pressure is the least. There is a low pressure inside this venturi. Now, if we remove 1/2 of the venturi and take it away, you're going to find now we have an airplane wing. And you'll find exactly the same thing occurs in an airplane wing. The air going over the top of the wing gets forced out of the way. It resists compression. By the way, if you put air in a gallon jug and squeeze it, you can compress it. But free air is incompressible. So if you force air out of the way, it doesn't compress at all. What it does do is speed up to get out of the way. And Bernoulli's law says, and here's the trick, Bernoulli's law says at places where the air is going the fastest, like over the top of the wing, the air pressure is less. So over the wing of an airplane, what you really have is a low pressure area up over the top of the wing and a relative high pressure area underneath the wing. And it's that pressure differential that creates lift. That's what makes the airplane fly. You have low pressure over the top of the wing, high pressure area underneath the wing. And that pressure differential will occur anytime the air is flowing smoothly over the surface of the wing and conforming to the surface of the wing. Now, let's you and I take a look at a couple terms the FAA wants you to know about. First of all, if you take a look at an aircraft wing, and if you draw a line from the trailing edge of the wing up here to the leading edge, that line is roughly called the chord line, and it points the direction the wing is pointed. Now, if the wing is going this way, the wind will be coming from the opposite direction. They call that the relative wind because it's the wind relative or in relation to the wing itself. And so if the wing is going this way, the relative wind will be coming the opposite direction. Now this angle between the chord line of the wing and the relative wind is called the angle of attack. And the FAA wants you to know that, and they call that an acute angle, meaning it's the small way around, not the big way around. The small angle here is called the angle of attack. Now, the FAA is going to ask you that terminology question, so let's you and I take a look at Figure 1, back in the back of the book, in the FAA pages back there, and they're going to ask you, what is acute angle A here? Well, here we have the chord line of the wing, here we have the relative wind. That angle is called the angle of attack. So that's one of the things you need to know, is angle A is called the angle of attack. Now, the angle of attack determines how much lift there will be on a wing. Let's you and I take a look at a wing actually flying in an airplane. Here's an airplane flying along, and we have it in a wind tunnel with smoke going over it. And as you increase the angle of attack, the lift gets greater. But however, I said there's only lift as long as the air conforms with the surface of the wing. Now, when you get the angle of attack so high, the air can no longer conform with the surface of the wing. And instead of flowing smoothly over the surface of the wing, it backfills and burbles and eddies. Lift is destroyed and the aircraft is said to have stalled. Now let's take a look at a close-up picture of exactly what we just saw there. We increase the angle of attack of this wing, and as it increases, we change the angle of attack. The relative wind can no longer conform to the surface of the wing, and when it separates from the surface of the wing, and then it continues and burbles and backfills and eddies, you're going to find that lift is destroyed and the aircraft is said to have stalled. Now, an airplane stalls at a specific angle of attack. The exact angle of attack at which the air can no longer conform to the surface of the wing is really designed into the wing. So an airplane stalls at the same angle of attack regardless of the gross weight of the airplane. So at what angle of attack does an airplane stall at? Always, for the particular airplane and configuration of the wing, always at the same angle of attack. So that's one of the things you need to know. Now, as you go to higher altitudes, there's thin air at high altitudes, but that thin air affects your indicated airspeed, your airspeed indicator, in exactly the same way it affects the wing. So would you stall at the same indicated airspeed at high altitude or lower? And you see it right now. The indicated airspeed at which an airplane stalls will remain the same regardless of the altitude. There's thin air at higher altitudes, but there's thin air for both the wing and the pitot tube, and they're affected exactly the same way. So it's the angle of attack that makes an airplane stall. Now, normally an airplane will stall at a specific indicated airspeed because unless you have some load factor on the airplane, G-forces on the airplane, it'll stall at a given angle of attack, and that angle of attack will always occur at a specific indicated airspeed. Now let's talk about spins, and this is an interesting example of spins right here. Spins are really exciting flight. That's fun, isn't it? All right. Well, maybe it isn't fun for some people, but that's a spin. Now, they're going to ask you on the test, what do you have to do to spin an airplane? Well, in order to spin an airplane, first it must be stalled. So you need to know if you want to avoid spinning an airplane, you need to avoid stalling that airplane. Now, they're going to ask you when an airplane is spinning, are both wings stalled or just one wing stalled? And the answer is, regardless of which direction the airplane is spinning, to the left or to the right, both wings are stalled. Why is it spinning, you might want to ask? Well, the reason it's spinning is because one wing is more stalled than the other, but both are stalled. So during a spin to the left, the FAA will ask you on the test, how are the wings? And the answer is both wings are stalled. anything that interferes with the smooth flow of air over the surface of the wing will change the way it flies. For instance, if you have frost all over the surface of the wing, you need to remove that frost because it can disrupt the smooth flow of air over the wing, and it will adversely affect its lifting capability. So if you get out to the airport and there's frost all over the wings of the aircraft, you need to take something plastic like a credit card or some credit card you want to get rid of because it'll break it up, and just scrape off all the frost off the wings of the aircraft. Now, frost which has not been removed from the wings of the airplane before flight may prevent the airplane from becoming airborne at normal takeoff speed. So you really have a problem, and you must remove the frost because it can cause the airplane to stall at a higher airspeed and also stall at an unpredictable speed. So you have no idea exactly when the airplane's going to stall. You and I both know that when we're taking off and climbing out in an airplane, we have to hold lots of right rudder. Here's a good example of a guy holding lots of right rudder when he's taking off here. Now, the question is, why do you have to hold right rudder when you're climbing out and taking off? And the FAA wants you to understand that really well. Well, the reason you have to hold right rudder is the airplane has a left turning tendency. And the reason the airplane has a left turning tendency, one of those reasons is P factor. Now, P factor has nothing to do with how long you've flown since you've gone to the bathroom. No, that's not what it has to do with. P factor has to do with the pitch of the prop blades. And when an airplane is in slow flight, like after takeoff or when you're climbing out, the nose of the airplane is pointed way up in the air like so, but the airplane is going forward on an angle about like this. That means the relative wind is coming from the opposite direction. And that means the propeller is not pointed directly into the relative wind. And the right prop blade, which goes down, winds up taking a great big bite out of that relative wind. The left prop blade, which ascends or goes up, takes a much smaller bite out of that relative wind, and that means the airplane wants to turn to the left, and that is called P factor, or asymmetric propeller loading. And it causes the airplane to yaw to the left when you're at high angles of attack. And they call that P factor, or asymmetric propeller loading. Now, the left turning tendency of an airplane is caused by, the FAA wants you to know, the propeller blade on the right producing more thrust than the blade on the left. Now, that left turning tendency is sometimes referred to as torque, T-O-R-Q-U-E, and they're going to ask you, when is torque the greatest, at high power or low power? Well, the propeller and the engine horsepower are what makes the airplane want to turn to the left, so at high power, definitely. High airspeed or low airspeed? And the answer is low airspeed, because that's when you have these high angles of attack with the nose pointed up in the air and the right prop blade is taking a bigger bite out of the air. And high angle of attack or low angle of attack? And the answer is high angle of attack. Now, normally, at cruise speed, an airplane does not want to turn to the left. And the reason for that is the manufacturer has built some aerodynamic compensations into the airplane. For instance, there's a little bigger angle of attack built right into the left wing, and a little smaller angle of attack built into the right wing, and the tail is canted a little bit to the right, and these aerodynamic compensations counterbalance the left-hand turning tendency of the aircraft. But when the airplane is slow, there's not enough air over the wings and tail to counterbalance that left-turning tendency, and also, when you have high power, there's more of a left-turning tendency. So, torque effect, that's the left-turning tendency, is greatest when? Well, it's greatest at low airspeed, high power, and high angles of attack.